Namaste. Namaste everyone. So while explaining interference, diffraction, polarization, everything, we took the help of wave nature of light. Light was taken to be a wave, and in order to explain polarization, light was taken to be a transverse wave, electromagnetic wave, in which electric fields can be confined to a particular plane. So it was a transverse wave. After all, it is a wave. But when light showed photoelectric effect, there was a confusion. Wave theory couldn't explain how photoelectric effect occurs. The practical aspect is already seen. Henry Hertz discovered that light, when it falls on certain metals, electrons come out, and that cannot be explained using wave theory, why it happens so, and sufficient proper explanation cannot be given using wave theory. So whether light is a wave or not, the question came into picture. And later on, already explained Max Planck's quantum theory. Actually, Max Planck proposed quantum theory to explain black body radiation. In first PU you have studied a black body emits radiations of different wavelengths, and there is a relation between temperature and the wavelength emitted, and it is inversely proportional to the temperature. The energy emitted is directly proportional to the fourth power of temperature, Stephan's law. So there is a black body radiation, and all those black body radiation was not explained by any theory. So Max Planck proposed a separate theory called quantum theory, in which he says energy cannot be continuous. You can't have any value of energy emitted by a body. It should be in the form of discrete packets. So every packet should contain an energy called E is equal to h nu, and it is called photon or quanta. So quanta is a packet of energy, and the energy of each packet is h nu, where h is Planck's constant, nu is frequency of radiation. So according to quantum theory, if you switch on a bulb, light is not emitted in all forms, all energies. So each photon coming from that bulb is identical, that's what it says, and each photon has got energy. More the number of photons means more intensity of light. So that was a different approach, because wave approach says that if anything is a wave, you can have any amount of energy from the wave. You can have more energy, less energy, continuous form of energy, there is no gap in between. But quantum theory says that if anything emits energy, that energy should be in the form of packets. That means if you have one, or you should have two, you will not have any energy in between that. So it appears in the form of discrete packets called quanta, and that theory was already proposed by Max Planck about in order to explain black body radiation. Now, when people started looking into the special feature of light, that is when light falls on a material, electrons come out, what you call photoelectric effect, when no theory could explain it, this quantum theory was fit enough to explain it, and that was Einstein. Einstein, when he came to know that there is a theory given by Max Planck, which is very fit enough to explain black body radiation. Why can't I use the same quantum theory to explain the photoelectric effect? So photoelectric effect is a phenomenon of light shown, and it was discovered by Henry Hertz. He found that light falls on a metal, as it falls on a metal, electrons come out. That is one thing. And Max Planck proposed a quantum theory in order to explain black body radiation, and now came the Einstein in between, and it is not his theory. That quantum theory is Max Planck's quantum theory, and the discovery is from Henry Hertz, that is photoelectric effect, and he in between came and explained that the theoretical aspect of photoelectric effect using Max Planck's quantum theory. So discovery from Henry Hertz, and theory of Max Planck, and explanation is from Einstein. So Einstein used quantum theory to explain the way in which photoelectric effect occurs, and that explanation was a very beautiful and very simple explanation. For so many years, that thing, how the photoelectric effect occurs, what is the theory behind it, that was unexplained. and that was beautifully explained by Einstein's explanations. And Einstein didn't use his own theory, he used quantum theory from Max Planck, and he didn't discover photoelectric effect. It was discovered by Henry Schwarz, but he gave a beautiful explanation for that. Finally, the Nobel Prize was won by Einstein for his beautiful and simple explanation of photoelectric effect based on the quantum theory. That means light is a packet of energy, it is not continuous form of energy like a wave. Now the question arises whether light is a wave or a particle. Whether it is a packet of energy like a particle, or whether it is a wave, it is a continuous form of energy. Because if you want to explain reflection, refraction, interference, diffraction, polarization, all those properties of light in a series, you can explain interference using wave theory of light, you can explain diffraction using wave theory of light, you can explain reflection, refraction, polarization, everything using wave theory of light. But when it comes to the question of photoelectric effect, when light falls on metal, electrons come out, you cannot use wave theory of light. You have to say that light is not a wave, it is a beam of packets of energy, and those packets of energy are called quanta, and you have to use quantum theory. Now the question comes whether actually what is light? Whether light is light is actually a packet of energy, or whether it is a wave, it is a continuous form of energy or discrete form of energy. Right? So if you want to deal with that, of course the people, it becomes very difficult whether light is this one or that one. So people came to a conclusion, and that light has a dual nature, right? Light has both the natures. It sometimes acts like a particle, sometimes like a wave. And wherever it acts like a particle, take quantum theory and explain that phenomenon. Wherever it acts like a wave, continuous form of energy, wave, take wave theory and explain it. So it has got a dual nature. So now what is photoelectric effect actually? So that made us to believe that light has double nature, right? Sometimes it acts like a packet of energy, sometimes it acts like a wave. Now what is actually photoelectric effect? Accidentally, Henry Schwarz and his followers Lenard and Hallwach, they were able to see that when light falls on a certain metal, and photoelectric current, electrons come out of the metal, and some current started enhancing when light fell on certain metals. So something should be coming out of this metal, and nowadays we have enough explanation for it, because electrons are revolving around the nucleus in definite orbits, and as they are revolving around, they will have some negative potential energy because they are bound to the nucleus. So they are tightly bound to the nucleus. Some innermost electrons are very tightly bound to the nucleus, whereas outermost electrons are not so tightly bound to the nucleus because they are far away from the nucleus. The bond or the force of attraction between electron, negatively charged, and proton is very less when the electron is far away in the last orbits. So it is easy to remove all those electrons. They are called valence electrons. And moreover, metals contain some electrons which are very free and moving around inside metal. They are called free electrons. And these electrons need a very less energy. And still, free electrons are not very free. They are bound inside the metal and they are not ready to come out. And if they want to come out, somebody should give an extra energy to these electrons. And when extra energy is given to these electrons, they can come out. So the energy with which these free electrons moving inside the metal, even though they are free from the bond from the atom. But they are not free to come out. Still they have negative energy. They are bound inside the metal. As if you have a large well, and suppose there is some acres of 1 acre of space inside the well. Suppose there is a well, very large well, and acres of space inside the well. People can play cricket inside, right? They can stand inside and play cricket, but still they can't come out. They are free inside, but they can't come out. So they are bound, still bound. Suppose they want to come out, somebody from outside, they must supply some energy and they have to pull them out. So still their energy is negative. So they have negative energy. Actually, we people on the earth have negative potential energy because we are bound to the earth. We are attracted towards earth. And if you want to go out, somebody outside from outside or somewhere else should give positive energy to us and they have to go out. Even if a rocket has to be launched from the earth and if it has to be made free, any satellite for that matter, some extra energy, fuel energy must be given, and then that has to be used to make that rocket or satellite to become free from the earth's gravitational pull. So you need an extra energy. So still they are in a negative potential energy. So somebody from outside, extra energy has to be supplied from outside, and then you have to become free. So with what energy they are bound? inside the material, or how much energy is required to remove them, and that is called work function of the material. So here we will get some terms. First term is work function. What do you mean by work function of a material? It is energy, so it corresponds to the minimum energy. Minimum energy required to remove an electron from the surface of a metal. You have to remove the easily available electron, most easily available electron. What is the minimum energy required to remove the electron from the surface of a metal? This is called work function. So you don't get any energy term here, right? Because work is energy, right? So from here onwards you have to pick it up. Work function is the minimum energy required to remove an electron from the surface of a metal. Sir, work function depends on what? Material. Some need more work function. What do you mean by that? In that material, the even least bound electron may be having most energy, right? Most negative energy. So you need more energy to be supplied to remove it. So some materials require more work function, more energy to remove the electron. Some materials require less work function, less energy to remove the electron from the metal. It is as if, suppose you have friends A, B, C, D. Friend A is having 25,000 rupees of loan in his bank, and friend B is having 30,000, friend C 50,000, friend D 75,000. So they are all bound to the bank. They cannot go move out unless they fulfill all the money to the bank, right? So if you are the fifth person, you are rich enough and you want to help your friends, then how much work and money you have to give them so that you can make them free from the bank bond, right? So if you want to make them free from the bank bond, you have to supply 25,000 to the first person because he is having 25,000 loan, 30,000 to the next person, 50,000 to the next person, 75,000 to the next person. So it depends on the person, depends on how much loan he has, right? Similarly, it depends on the material. Work function depends on the material. From material to material, it may keep on varying. But in a material, it is not different for different electrons. Most of the electrons will have the same. There is a small difference, we will see that later. So electrons have the same work function. For example, if in a metal, if you can supply, suppose this is a metal piece and electrons are on the surface, say, they can't come out, and if you can supply energy and you can remove the electrons by supplying an energy of, say, some 20 into 10 to the power minus 19 joules of energy. Supply this much of energy, remove the electron. Then what energy is required to remove this electron? Same. What energy is required to remove this electron? Almost same. There may be a small difference depending on the position of electrons, but still you can say that it is almost same. For a material, work function is a constant. But material to material, work function may change. Okay, one term, the minimum energy required to remove the electron from the surface of a metal is called work function. Then, okay, so I'll write that in photoelectric effect. I'm dealing with this. Okay, we will write it later. Now, in what way you can supply this energy? That is the second question. If a material contains free electrons, electrons say, sir, I want to come out. Please supply some energy to me. I want to be free. I want to come out of the material. Then you ask, what is your work function? Sir, I need so much of energy. I need some energy to remove, to make myself free and come out of the material. Okay. Then, how do I supply energy to the electron? You ask the electron, in what way you need the energy? Sir, give me the energy in the form of light, sir. Another electron says, sir, I need energy in either in the form of light or heat also. Heat is also a form of energy. Give energy in any form. Accordingly, electrons come out. Now, after coming out of the material, you ask one by one electron. Electron 1, how did you come out? Sir, I came out with the receiving energy in the form of heat, sir. I came out by receiving energy in the form of light, sir. What about the third electron? It says, sir, I came out by receiving energy in the form of electric field and magnetic field. And the fifth electron says, or another electron says, sir, I came out by receiving energy from another electron, sir. If you want to remove one mango, if you don't have anything else there, only mangoes fallen in under the tree, no stones at all, what you will do? Take one mango and throw it to the other mango so that you will have two mangoes then, right? So if you don't have stones, mango itself is the best choice to remove another mango, right? How to remove an electron? from the surface of a metal. Take another electron. So hit it to the target. When fast moving electron is made to hit the target, fast moving electron will have kinetic energy, and that kinetic energy will be transferred to the material, and electrons inside the material will absorb that energy and they will come out, right? Suppose your friend is not ready to climb up the upstairs. What you can do? You ask your friend to stand. So he is not ready to go here. He is very fat and he is very lazy and he is standing here. Now what you can do is, you are thin, say, but still you want to remove him. You want to throw him to the upstairs. So what you will do? You just come running with such sufficient high kinetic energy and just hit him. Go and hit him with such a high kinetic energy that your friend will be thrown here and he will come here, right? So you can do that. You can remove one electron by using another electron. So in that way, we have different types of electron emission. Types of electron emission. How did you supply the energy? Types of electron emission. One is photoelectric emission, the same one. What do you mean by photoelectric effect or photoelectric emission? Supplying energy in the form of light. Photo means light, right? Supply the energy in the form of light, then remove the electron from the surface of metal, but your supply of energy must be enough to remove the electron. That means you have to supply an energy at least equal to work function or more than the work function. Whatever it is, let the energy be in the form of light. So if the energy is supplied in the form of light and electrons are removed from the material, then such a type of emission is called photoelectric emission. Supply the energy in the form of heat and remove the electrons from the surface of the material, and then it is called thermionic emission. Energy supplied in the form of heat. And third one, supply the energy in the form of electric field and magnetic field and remove the electrons from the surface of a metal. Electric or magnetic field. So that will also remove the electrons from the material. That is, suppose you hold a material in a very strong electric field, electrons may come out. So that is field emission. What about last one? Secondary emission. Just now I have told. Suppose you don't have anything else. Take an electron, make it to move very fast, hit it to the target. When the electron hits the target, it loses all its kinetic energy. Who will gain that energy? Electrons inside the material will gain the energy and they come out. So supplying the energy in the form of an electron and removing another electron from the material, that is called secondary emission. So these definitions are important and very easy to remember. I think you can do that, right? So what is photoelectric emission? When energy is supplied in the form of light, and electrons are removed from the surface of the metal, that is called photoelectric emission. If the energy is supplied in the form of heat and electrons are removed from the surface of the material, then it is called thermionic emission. If the energy is supplied in the form of electric field and magnetic field, then electrons are removed, field emission. And if a fast moving electron is made to hit the target and electrons are removed from the material, that is called secondary emission. So throwing a mango and taking another mango from the tree. So that is another one, secondary emission. Now we will concentrate on this first one, photoelectric emission. So what is photoelectric emission? And of course, work function definition is important. The minimum energy required to remove the electron from the surface of a metal, it is called photoelectric emission. Why do we call surface of a metal? Because remember, we are not removing an electron which is in the innermost orbit of the nucleus, around the nucleus, not in the nucleus, around the nucleus. Because if you want to remove an electron from the innermost orbit around the nucleus, it is very difficult because it is very tightly bound to the nucleus. Removing outermost electrons itself is a difficult task, but it is possible. Valence electrons can be removed and free electrons are easily removed, and that can be done using this process. Okay, work function, minimum energy required to remove the electron from the surface of a material. Now, how did this Hallwach and Lenard, they did the experiment and they got this idea. So Heinrich Hertz observed this, but the experimental these observations, what happens when light falls on a material and all those things, these observations were given by Hallwach and Lenard, two scientists, Hallwach and Lenard. What is their experimental observation? So this may be the next question in this chapter. Explain the experimental observations of our experiment done by Hallwach and Lenard. Okay, what experiments did they do? First of all, you should have a material which emits electrons, right? And you should make a sufficiently energetic light to fall on this, because we are concentrating on photoelectric effect. You should have a sufficiently energetic light. Remember, energy E is equal to hc by lambda. H nu is the frequency. Energy is inversely proportional to wavelength, and from here onwards you should have a very clear idea about the electromagnetic spectrum. Right? Light is a part of what visible light is a part of electromagnetic spectrum, and in electromagnetic spectrum you have gamma rays. Okay, this is very, very important, because without this knowledge it becomes very difficult to understand the things. Gamma rays, and then you have, you can see here, right? Gamma rays, X rays, ultraviolet rays, and visible, then infrared, then microwaves, radio waves. So we have like this, right? If the things are like this, this is having least wavelength and most energetic, and a wavelength is increasing in this direction. This is least wavelength and this is most wavelength, radio waves. Okay, so this is how it is situated. Now if you concentrate on these three, that is enough for me. Most energetic are gamma rays. Gamma rays are very, very highly energetic radiations, and if you expose your body to the gamma radiations, they will kill the cells, and they will change the genetic property of the nucleus, and that is very hazardous to the living beings. So we hate nuclear weapons. Why? Because once the nuclear weapons are used, once the nuclear bomb is blasted, what are all the ingredients or the products that we get after the explosion? They are highly radioactive. They emit gamma radiations. And these gamma radiations will be existing in the materials remainings of the bomb for a long time. And if you are exposed to those radiations, that will cause numerous diseases. And moreover, you will get the disease as well as your generations will also get the same disease, and the problems will be carried to the offsprings later. So that is why we hate it. Suppose we fight with sword and other things, no problem. The persons who are fighting will be affected. Person who is in the house will not be affected. But what about nuclear radiations? They affect the generations and generations coming next. So that is the problem. So gamma radiations are very, very energetic. They can kill the cells. That's why gamma radiations are used for the treatment of cancer. When they attack the cancerous cells, the extra multiplied cells, they are injected there with the gamma rays. Gamma rays kill them. Okay. Then X-rays are also highly energetic, but lessly highly energetic compared to gamma rays. But they are still highly energetic. Ultraviolet comes next one. They are also injurious to living beings, but some part of ultraviolet light is not so injurious. So you can tolerate it, because some part of ultraviolet light is needed for us, right? You should get exposed to the ultraviolet light. People say that once you wash the cloth, you should dry it using sunlight, right? Not inside your house. You should put it outside. So when you put it outside, ultraviolet radiations fall on these clothes, and they will kill the small microorganisms. Ultraviolet light can kill the microorganisms. That's why you should get exposed. And even ultraviolet light, when it falls on your skin, it creates vitamin D. So otherwise you won't have enough amount of vitamin D. So that is the specialty of ultraviolet light. But still it is energetic, but visible radiations, compared to visible radiations, ultraviolet, X-ray, gamma rays are all highly energetic. Okay, now come to this point. Hallwach and Lenard, they did one experiment. They took a photosensitive plate, on which when you put some energetic radiation, you get electrons come out. Now this series is very important. Why? Because suppose you are asked a question. When ultraviolet light is put on a material, no electrons came out. What is the next radiation you will try with? Is it visible or X-ray? That is what is. If ultraviolet radiations are incident on a material and electrons don't come out, what is the meaning? That what the energy you have supplied is not enough work function. There is a minimum energy required to remove the electron. You have paid 10,000 rupees to your friend, but still he has not come out of the bank's bond. Why? Because he has 25,000 loan. That is not enough. So he rejects it. Your friend says, I don't want 10,000. If you want to pay me 25,000. That is what is called quanta. He doesn't want to receive anything less than 25,000, because if you give 25,000, his loan will be cleared. So in the same way, this, when you supply a visible light or ultraviolet light, say, if the electrons don't come, means that energy is not sufficient to come out of the material. So what happens is, you have to try for the next energetic one, X-rays. And even for X-rays, if electrons don't come out, then you have to try for gamma rays, like this, right? So you have to keep on increasing the energy, decreasing the wavelength. So as wavelength is decreased, energy keeps on increasing, remember. As wavelength is decreased, energy keeps on increasing. So decrease the wavelength, increase the energy. So that is the higher wavelength spectrum, and this is the lower wavelength or higher energetic spectrum end. So this should be very clear, and every now and then I will be remembering this, so you must be able to follow this. Now take a pen and paper, try to write that experimental setup for explaining photoelectric effect. That is what I need of. You must take a pen and paper, you have to write it, otherwise that diagram, if you by heart it, it is of no use. Okay, so Hallwach Lenard's experiment. Yes. So they took one photosensitive plate, right? That plate on which when light falls, electrons come out. Photosensitive plate. And after the electrons come out, you must be very sure that electrons have come out, because you can't see the electrons which have come out. How to see whether the electrons have come out or not? What the thing is, you make those electrons to flow through a wire. Then if you get a current, then the electrons have come out and they have moved in a wire and they have produced current, right? So you need a path to attract the electrons. Okay, so you should, and for all these things should happen, you do all these things in an evacuated chamber. That means there is no air, vacuum. Because when the electrons come out, when they move out, if they find something gas or anything, they will start colliding with the gas molecules. They lose energy. So you can't detect the electrons so easily. So better you create all these photoelectric effect phenomena in vacuum. So let us first of all take one evacuated chamber like this. Let us take one evacuated chamber, right, like this. So it is a vacuum chamber, right? So, and here is a window just to put the light into, and this is a quartz window. I'll write it. So as I do this, you do it, right? Quartz window. Hope you are ready with the pen and paper. So there should be an evacuated window, because we don't want electrons after they come out lose their energy, and let them not collide with the gas molecules, let them be free outside. So, and we should have a cathode C, which emits photoelectrons when light falls on this, right? This is cathode C. And here is an anode, right? This is anode, which receives the electrons, because otherwise I have already told, if electrons are moving somewhere, our eyes can't see that. If you want to see this, make the electrons to flow through a wire and convert it into current. Flow of charges produces current, right? Rate of flow of charges is current. Okay, now why it is quartz window? Because for us the best suitable energetic beam is ultraviolet, because ultraviolet is energetic as well as it is little harmful, less harmful compared to X-rays and gamma rays. So we will take ultraviolet, which is energetic enough to remove the electrons, and which is not hazardous to the living beings. And such a beam of ultraviolet is made to pass and hit on the surface. And this is ultraviolet light. This is the source of ultraviolet light. Shall we? Shall I rub this? I think you can remember these names, Hallwach and Lenard experiment, right? So I will, this is the source of light, and this is ultraviolet light. Sir, why quartz window? Why this is quartz window? Ultraviolet light, I was discussing in one of the class. Ultraviolet is completely absorbed by glass, ordinary glass. So if this window is made by glass, when I put the ultraviolet, it will be absorbed by glass. It doesn't enter and fall on cathode itself, cathode at all. So you might have seen people welding iron rods, right, in workshops. When they weld, lot amount of light is produced. It contains visible light as well as ultraviolet. So if you don't wear anything which is made up of glass, directly look into that glare of light. Ultraviolet will enter into your eyes and it will create harm to your eyes, and your eyes will get paining. You will feel paining after some time. So in order to avoid it, they will be holding a glass or wearing goggles, because glass completely absorbs ultraviolet and protects our eyes. So if you are using ultraviolet under unavoidable situations, then this should be a quartz window. I think I was saying about increasing the resolving power of a microscope by reducing the wavelength of light coming from the object. Remember, when the light from the object is illuminated, when the object is illuminated with a lower wavelength light, resolving power increases, because resolving power is 2n sin theta divided by 1.22 lambda, correct? For a microscope. N is the refractive index of the medium between the object and the objective. Theta or beta is the angle, semi-vertical angle of the cone of rays. Remember this one? And lambda is the wavelength of light coming from the object. So ultra microscopes use ultraviolet light to illuminate the object. So we have a separate ultraviolet light to illuminate the object, and that lambda decrease will increase in resolving power. But the problem with the ultra microscopes is, if you use glass lenses and glass prisms in the microscopes, ultraviolet light is completely absorbed. So lenses and prisms used in the ultra microscopes should be made up of quartz. That is why we have quartz window, right? Quartz doesn't absorb ultraviolet, whereas ordinary glass absorbs ultraviolet. Okay, that is over. Now light falls on this cathode. Cathode is photosensitive, and what the energy we are incidenting on this is enough to remove the electrons. So electrons are removed and they move out like this. Like this. They will be moving out. These are all electrons. And these electrons must be attracted. So this should be given to the positive of the battery, because electrons must be attracted. And these emitted electrons shouldn't come back. So this should be given negative of the battery. Negative of the battery will have negative potential and it will oppose electrons. Electrons are negatively charged. Positive of the battery will attract electrons. Now we have to connect this to a battery outside. So this is evacuated chamber. So as I do that, you keep on listening and writing. All the things must be done at the same time. So this is cathode and this is anode, evacuated chamber. Okay, now I have to use an arrangement here. While explaining photoelectric effect, and I have told already, if this should not be given negative, right? If this is given negative, what happens? These electrons will be repelled. Electrons won't go at all. We will not be knowing whether the electrons are emitted or not. They must be made to move through a wire, and we have to measure the current. That means this should be given positive. But in order to do some experiments, sometimes we need to give negative also here. So we need a commutator. What is a commutator? Commutator is an arrangement where we can change the direction of current. Right? So how the commutator is done? It is just 3 switches like this. That's all. You will understand what is a commutator later. Okay, I will connect it here. 3 switches like this. Okay, like this. Sir, where will you connect it, sir? This is connected here. Okay, and what about this one? This one is connected here. So I will bring this. This is very close now. It appears very confusing. So I will do it like this: 1 set, 2 sets, 3 sets. Okay, I will connect this one. I will interchange them. Yes, I will do this one here. Yeah, and I will do this one, a jump here, and this one. Okay, this is okay. I take a new chalk. No chalk around. I will, yeah. Should I take a different color chalk? No, okay. Right, so this is enough. Later, see, jump this one here, connect this one here, and connect this one here to this switch. Sir, what are all these connections? Looks very horrible? Not horrible. It's very beautiful. Later on you will come to know that this is very beautiful. Okay, next, of course, sir, you have not given any battery saying that this is positive, negative and all. Okay, I have not given any battery. Now get ready with the battery. How? You connect a rheostat. What do you mean by rheostat? A long wire, right, like this, so that you can take any turn of the wire and you can change the current. And a battery like this. So battery positive, negative, positive, negative, positive, negative, like this. Finally ending at negative, positive, negative. Now connect this one directly here and connect this and here. Like this. Enough. Now when I change this position here, current keeps on changing. That's what I can do. Okay, so I should have shifted this still up because I need more amount of space. This one, this one, this one. Okay, commutator key, this one directly connected, this one here. Okay, okay, it is not here, it is connected here. Sorry, not this connection. It should be here, one connection, here another connection. Now it is correct. Right? To the middle two keys, you connect this battery set. What do you mean by battery set? A battery connected to a long wire. Sir, why do you connect it to a long wire? Because I want to change the current. If I want to change the current, I keep on moving this contact here, 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 anywhere. I can change the current. That's all arrangement. Suppose you have a battery like this. If it is 5 volt battery, say, and if I connect it to a long wire, like this, or a resistor, I get 5 volt here, and if I take a voltmeter, it is very simple experiment. If I take a voltmeter and connect it from here to here, it measures 5 volt. If I connect the voltmeter here, it doesn't measure 5 volt, it measures less than 5 volt. And if it is in the middle, it will measure 2.5 volt. If I measure it here, it may measure only 2 volt. When it is connected here, it may measure only 1 volt, depending on the length of the wire. So as the length of the wire is different, resistance is different, current is different, voltage is different. Okay, that is the beauty of rheostat. This is actually called rheostat. So for the time being, you take that this is just to change the current. See, this appears to be complicated, but in the next class also I am going to draw this again. Don't worry. And again you have to draw along with me. Try it 2 or 3 times in your house, and you do it with some a theoretical background. Don't simply by heart it. Okay, so what you have to do is you have to take an evacuated chamber, and that is connected to the 2 terminals of the commutator. So this is commutator. Today I can teach you only the theory part, sorry, the diagrammatic part, not much more than that. This is commutator, 3 switches like this, and the last switches are crossed here. First and the last switches. Middle switch is connected to the battery set. You be ready with the battery and a wire and connect one end to the variable end and here directly to the positive. Okay, now it is ready. Sir, how does it emit electrons, and which is positive and which is negative, sir? Now out of the 2 gaps here, you have 2 gaps, right? One gap is this one, another gap is this one, and here one set of gap, another set of gap, totally 4 gaps. You are allowed to select only 2 gaps, not all the 4 gaps. Now let me contact this gap and this gap, this one and this one. I will have some keys, and I can put the key and connect them, make them short. So I can put the key here and connect it, put the key here, connect it. Now what is the connection, you see? What about cathode now? Cathode is connected here, you see the path. Cathode is connected here like this. Of course, it cannot come here because it is open. So cathode from here, 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 like this, and it is connected to the negative. Am I right? It is negative. What about anode? Anode from here connected like this, like this, like this, like this to the positive. Is it okay? This is positive of the battery, this is negative of the battery. Shall I move it again? See, cathode from here like this, connected to the upper point. I can't come here because I can't go anywhere else. Open, open. So I have to come here, I have to pass through this because this is connected like this, like this, like this to the negative. What about the anode? Anode from here, it is connected like this, like this, like this, like this to the positive of the battery. If you want to write the polarity of cathode and anode, so I told cathode is negative and anode is positive now. See, cathode is connected here, here, here and here like this and to the negative, right? So this is minus. Am I right? What about anode? So I will follow it again. Anode from here, jump here like this and it is positive. This is positive. Right? So they are given negative and positive. Now even if the electrons are emitted from the cathode, they don't return back because already they are given negative potential. What about anode? Anode is given positive, so electrons are attracted towards it. So it is okay. Now if you want to change the direction of current, then you have to get the help of commutator. What is commutator? Commutator is a device which is used to reverse the direction of current. How do you reverse the direction of current? Simply change this position of this connection. So you remove this, open this and connect the lower gap. So I will connect this and here, this one, yeah. I will connect this and this now, this gap. Last time this was connected, now this time I will connect this one. So in a commutator you are supposed to connect only the two opposite gaps. Either these two opposite gaps or these two opposite gaps. Now you see the polarities get interchanged. How? Very simple. Now start from here. Cathode like this, like this, like this. I can't jump here now because it is open. So from cathode coming over like this, coming like this, like this, like this. It is positive now. Like positive. What about here? Anode. Anode coming from here like this and I have to go like this now. I can't jump here, go like this and it is C. It is negative. Negative. Reversed. Now electrons can't go here because they have been repelled by this anode. So if you want that thing to happen, you can do it here. Simply you need not change the circuit. Simply just change the switch here. So now let the switch be in the ordinary position. Let the switch be here. Here, here. Now how is the situation? This should be negative. This should be negative and this should be positive, correct? From here cathode like this, negative. From anode, from here like this coming, yes, positive. Yeah, positive. Now, cathode is given negative, anode is given positive. Light of suitable frequency is made to fall on this, say ultraviolet light. Electrons are emitted and these electrons come out of the material and they start moving towards the anode because anode is given positive potential. Anode clearly attracts these electrons and these electrons will start moving in the circuit, and now these electrons will start moving somewhere. For example, it is connected where it will move like this and this one here. So I will connect an ammeter here. Which ammeter? Very, very sensitive ammeter. It is a microammeter. And I can connect a voltmeter also here between this, so that I need to find out how much voltage I am supplying. Okay, this completes the circuit. This, and for this last connection it is over. And plus minus, okay, this is plus and the other end is minus, and when I move it from here minus, this is plus. This much you have to write. Minus because we come from here, the minus can come, minus side of the ammeter should come first. When you come from here, plus side, you see, from plus, plus. This is starting from minus, so this should be minus. Okay, so this microammeter will start showing the reading. Why? Because we are supplying enough amount of light, and that light is making the electrons to pass, to be emitted, and these outcoming electrons are attracted by the anode. Anode gives sufficient current. This is only the introductory part, right? The first part of this experiment, how the circuit is constructed and what happens in the circuit. That's all. So we get sufficient amount of current, and that current obtained because of the motion of electrons is called photocurrent. Okay, photoelectric current you can write, and the electrons which are emitted during the photoelectric emission are called photoelectrons. So photoelectrons are emitted and they are received by the anode, and we get sufficient amount of current in the circuit. Now Hallwach and Lenard, Hallwach and Lenard, they did the experiment in different ways. They started changing the frequency of radiation with the different frequency, more frequency, less frequency. They changed the intensity of radiation and started observing what the changes are occurring here, and then derived many ideas behind this. And when the frequency of incident radiation was increased, it was found that there was no change in the current, and when the intensity of incident radiation is increased, there was found to be a change in the current. And before that, you must know what is frequency and what is intensity according to quantum theory. Now I already have given you an idea. E is equal to h nu is equal to hc by lambda. According to quantum theory, light is a packet of energy, and each packet of energy should have an energy E is equal to h nu or hc by lambda, where nu is the frequency and h is a constant called Planck's constant. Right? These things are very important in this chapter. And sc is velocity of light in vacuum. Okay, lambda is wavelength of light. Now, lesser the wavelength of light, more is the energy. More is the frequency, more is the energy. So energy is directly proportional to frequency, but inversely proportional to wavelength. Right? That is one part which is very important. That is, so if you are given a beam of light, suppose I give you a source of light, how to increase the energy? You have to change the frequency itself. Increase the frequency or decrease the wavelength, it is one and the same. Thereby you can change the energy. Sir, how to increase the brightness, intensity? So there are two things involved in a light, either changing brightness or changing energy. What do you mean by changing energy? Changing energy means you are changing the energy of each packet. Okay, I'll rub this now for the time being. In the next class I will draw it again. You may not be having the full idea of this experiment now. We are going to deal with this experiment in the next class. So in the whole class, next class, we are going to discuss about this experiment. But for the time being, so energy, so quanta, and we are dealing with packet of energy called quanta. Energy of each packet is hc by lambda, that is h nu. What about brightness or intensity of light? You say that some light is very bright. What do you mean by that? Brightness or intensity? Intensity is a different factor. Suppose you have a bulb of one color, say blue color light. Where is blue chalk? Yeah. Suppose I have a blue color light, right? So this is the filament. It is switched on, and if I have a yellow colored light, or okay, I have yellow colored light. I think you can see both of them. So this is a filament. Now, what is different for these lights? Say same brightness. Both have same brightness. So this should be very clear if I want to explain you the process of photoelectric effect. Suppose you have two bulbs, one which is emitting blue colored light, another emitting yellow colored light. They have different wavelength, lambda 1 and lambda 2. They are different. They are not one and the same. What about frequency? Different. Lambda 1, lambda 2 different. What about frequency? Nu 1 and nu 2 different. Wavelength different. Frequency different. What about brightness? Brightness same. So intensity 1, I'll write it like this. Intensity 1, intensity 2, they are same. Right? I have taken same brightness. Now, what about packets of energy? You take a quanta, packet of energy coming out of this, right? Its h nu 1 is different from the quanta of energy coming from this, packet of energy coming from this, h nu 2. It is different. hc by lambda 1 of this one is different than the hc by lambda 2 of this one. because lambda 1, lambda 2 wavelengths are different, frequency different, so energy different, energy different. Energy of each packet is different here. So energy of this packet, suppose I say this as energy of this packet is E is equal to h nu 1, E is equal to hc by lambda 1, E1, and if energy of this packet is E2 is equal to hc by lambda 2 and E2 is equal to h nu 2, E1 is not equal to E2. Lambda nu 1 is not equal to nu 2. Lambda 1 is not equal to lambda 2. They are different. They are different. Only intensity is same. What do you mean by intensity is same? That is the question now. Regarding packets of energy, quantum. Now if I observe one packet of energy here, take one packet of energy here, these packets of energy are different because colors are different, wavelength different, frequency different. And each energy packet is different. But intensity same means, the meaning of this is number of photons coming per second emitted per second is same. Brightness, intensity of a light is referring to the number of photons coming out of the source. If 100 watt bulb is more brighter and 40 watt bulb is less brighter, the meaning is, in that case, intensity is different. Number of photons coming out of those bulbs are different. So that we will deal here. Intensity. Suppose if I have two bulbs which are emitting red color light. Suppose this is a filament and this is also red colored light. Okay, this is a filament and this light is more brighter, this light is less brighter. You can understand it. So this is less brighter, this is more brighter. What do you mean by that? What is the wavelength of light coming from this bulb? It is lambda, this is lambda, same. Because both are emitting the same color light, you can't have lambda different. Same, exactly the same wavelength. What about the frequency? Nu, same. What about the energy? Energy E, same. I am calculating per photon. Each photon will have the same wavelength, each photon will have the same frequency, and each photon will have the same energy. There is no difference in the energy, wavelength and whatever frequency. But what about brightness? Suppose this is a 100 watt bulb and this is say 40 watt bulb, less brighter. Only the thing is number of photons emitted per second is different. This is different. Why this is more brighter? It emits more number of such photons per second. Similar photons are emitted by 40 watt bulb. It emits less number of photons per second. That's why it is less brighter. But if you take one photon from here, one photon from here, photons are identical because both are having the same wavelength. So energy, intensity is energy emitted per second per unit area. That is intensity. So intensity, energy, so you must have a very clear idea about this. Remember, every bulb, every source of light will emit packets of energy. When you compare the two bulbs, if one packet of energy and another packet of energy are identical, then the wavelength of light coming from each bulb is different. Energy of each packet is if the wavelength of that packet of energy coming from first bulb and second bulb are different, of course then energy is different, wavelength is different. But if the number of photons emitted per second are same, then the intensity are same, right? Brightness may be same here, same brightness, but wavelength different. This is blue, this is red, yellow. So intensity same, but energy different, wavelength different, frequency different. But if the two bulbs of the same wavelength but having different brightness, then same wavelength corresponds to same energy, same frequency, but number of photons emitted are different, right? So if I compare two bulbs, say for example 100 watt sodium lamp, 100 watt sodium lamp and 60 watt mercury lamp. What is the difference between them? What the things they have same and different? 100-watt sodium lamp and 60-watt mercury lamp. Everything is different. This is sodium lamp, this is mercury lamp. H nu is same, lambda different. Lambda of this is different, nu is different, right? Nu different. Yeah, E energy different. Correct? Intensity is also different because you see the power, energy emitted per second, intensity different. Everything is different. Suppose you compare both 100-watt bulbs. One is sodium, 100-watt sodium, and 100-watt mercury lamp. What is the same? Sodium and mercury emit different colored lights, so wavelength different, frequency different, energy per photon different. But what about intensity? Same. Brightness same. Same brightness. Correct? And compare 100-watt sodium lamp and 40-watt sodium lamp. Both are sodium vapor lamps. Both are emitting energies, packets of energy same, because both are having the same wavelength, same color, same wavelength, same frequency, same energy, but watt different. Energy per second, intensity of light is different. Number of photons coming per second are different. So this idea should be very clear. So one is formula, E is equal to h nu, hc by lambda, and energy depends on wavelength and frequency. Energy is directly proportional to frequency, inversely proportional to wavelength, and intensity means number of photons emitted per second. So with this idea, we will move on to the next class. So keep all those things in mind. Only that examination point of view, examination corner, you have what is photoelectric effect, what are photoelectrons, and what are the various methods of removing electrons from a material, thermionic, photoelectric, field emission, secondary emission, what is work function, and the diagram. But we are going to study the diagram in the next class also. So keep reading this. Of course, this chapter is so beautiful that you can read it yourself also if you are interested. But if you have some problems, you can listen to the class and you can move on. So very important chapter, dual nature of matter or dual nature of light. We will keep on moving, and we will see it in the next class. Thanks for watching my class. Thank you. Thank you.